In this video, we're going to learn about linked list, which is a very useful data structure used in many applications. So let's see together that what is a linked list and how we can define or use different types of the linked list. So for drawing the linked list, I'm going to use this shape here. Here is an example of a linked list, which is some nodes that are connected to each other. So each of these boxes that you see here is called a node. So node, node, and a node. And that's why we call it a linked list, because there are several nodes that are connected to each other through a chain of so we can access one node after each other. In the linked list, the very first node of the linked list has a special name or a nickname. We call the very first node the header, or just head. So the very first node is called head. What's inside each node? Each node can contain some data. For example, it can store student information, it can be insurance information, or it can be just as simple as just some integer numbers. So the very first node head, then the chain of nodes that are connected to each other. The shape or the drawing that you see here is called a single linked list, because every node is connected to the next one. So here is, let's say, call it the node 1. This is going to be node 2, node 3, and this is going to be node 4. And as I said, node 1, because it is the first node, will be called the header node. So you might say, okay, how we can implement a linked list in a language such as Java? So first of all, we need to create a node, because node is the main part of a linked list. And a chain of nodes creates the linked list. So in Java, we can create a class called node, and we want to make sure that this node can store a variety of the data. So we don't want to just for example, create a node which is only a string, or maybe just the student information, or maybe just numbers. So that's what we call a generic type. So our node class will be generic. And that's how we're doing or defining a generic type in Java. So here inside these notations here, we are putting a letter such as T, or usually E, or any other letter to say that that's going to be the type of the data. So then we're starting with the curly braces, and now our data of each node will be from the type T that we just used here. So I'm going to call just it data, or data. And then, as you see, each node has some data, which will be here, plus this link to the next node, which is, as you see, the next node of a node itself is a node. So node, which is generic, and then I'm going to write next. So here is a very simple version of the class node, which is generic, and the data is from the type T, and the next node of the node is also a node with the generic type, which is generic and is T. So now you might ask, okay, how we can actually now define the linked list? So as I said at the very beginning, you see that the very first node of the linked list is called header, or head. And by using the next and next and then next, we actually can access every other node in the linked list. So here is a very simple version of the class linked list, which again will be a generic class. So linked list from the type T, and then I'm going to store the header, which is a node. So I'm going to first put the type. It's going to be a node, from the type T and head. So again, that's a very simple version of the single linked list. A linked list which has the first node, which is called head, and each node which has data from the type T, and the next node which is next, and again its type is from the node type T. So with this linked list that we have here, we're going to see what are the operations that we can do. For example, if we want to insert a new node, if we want to delete an existing node, or we're going to search for an item. And we're going to see that comparing to an array, which operation is faster in which data structure. For example, if the search operation is faster in an array, or it is faster in a linked list, or maybe insertion or deleting an item, which one is faster. So let's see together which the different operation they might have. So the very first one is to insert a new item into the linked list, which is insert front, or what we call it push front. Or what if you want to insert at the back, or push back? So let's see this one. For both the front and back insertion, there are several scenarios. For example, what if the linked list that we're going to insert a new node is already has some data, or what if the linked list is empty? So we're going to start with the case that the linked list is empty. For this case, if the linked list is empty, it means that there is no node. In other word, it means that the header node is null. So it exists, but it is null. So what we're going to do, we're going to implement the push back function, push front function. So push front, and we're going to insert the data. Let's call it D. So we have a data called D from the type T, and we're going to push these data to be the very front of the linked list. So we want to check if the linked list is empty, and that's going to be with this if statement. So if header is equal to null, that means that the node head does not exist, or the linked list empty. Then this node that we're going to create will be our first node, or in other words, it's going to be our header or head. So head will be equal to the new node, and again I'm using the Java syntax here, and with this data that we have here. So although I have not defined the constructor with one parameter in the class node, but I already used that. But what we can do, actually, we can go to the class node, and we complete our class here. So just to declare and making sure that we know, so here's going to be my constructor node with the type T and the data. And here are what I'm going to say. I'm going to write data be equal to D. And also I can say next be equal to null, although by default it's gonna be null, but just to be sure, I'm writing the next to be equal to null. So that's a very simple constructor. For sure you can create more than one constructor to also set the next node as well if you want. Okay, so let me delete some of the stuff here. So we have the this constructor here with the next we're going to be equal to null, and the data which has been set to null to D. So next equal to null and data equal to D. So that's for the case in which the header is null, which means that the linked list was empty. So what if the linked list is not empty? So we're going to write it's going to be else. So that means that I'm going to put a comment non-empty list. or linked list. So when the list is not empty, we're going to see that how does it look like. I always suggest to draw some some examples to see that how it works. So if the linked list is not empty, it means that at least there is one node in the linked list, which the first one is called head, and also I might have some other nodes in the linked list. Here we don't care how many items exist, but we know that at least there is one node in the linked list. And we're going to call the push front, which means that the data that we're going to insert will go to the very beginning of the our list. So here I'm going to assume that this will go here. This is the new node which is going to store the data ID. So with this shape, it helps I'm able to actually see how visually it works. So as you see here, this node D is standalone here, but it needs to be connected to the very first node here. That means I need to make this connection here. So first of all, let's create this node and let's call it node N with the data D. So going here, and I'm going to write node N equal to new node with the data D here. Then I need to create this connection. As you see here, the next node of the node N is the header node. So I can write N dot next equal to head. So I create the node N, which is correct. I made this connection, which is this one. So check. And now, as you see here, I need to fix something. We said the header node is the very first node, but now the header is the second node. So what I need to do, I need to just remove this nickname from the old header, and I need to put the N to be the new header. So, and that's how it's going to work. I want to just say N to be equal to N. Again, that's a very simple version of like writing the code. You might like write it differently, or maybe in a more efficient way. But again, just for the sake of examples of how it works. So that's a method called push front, which inserts a node at the very beginning of a linked list. Now let's see that how it's gonna look like the method of the push back, which means that we're gonna insert a node at the very end of the list. So again, we're gonna assume two scenarios, which is for the case that the linked list is empty and for the case that the linked list is not empty. So this time I'm gonna create the node N at the very top. So node N is equal to new node with this data D. Again, I'm going to check if header is equal to null, which means that linked list is empty. Then header will be equal to N, and we're done. Otherwise, I'm going to again just draw an example. Otherwise, let me try better calibrates. So here's an example of a list which has at least one node with a header. So in this example we have 3 nodes, and we're gonna insert the node N. So the node N with this data D will be the very last node, as you see here. However, I don't have access from the header to the very last one, because as you see here, this node N must be after the last node. So I have to traverse the linked list from the very first node to the very last node, which is this one. So that's called the traversing. So from the very first node to the very last one. How can I do that? By maybe creating a temporary node, which is going to be like the node that I am currently in or that I'm visiting now. And at first, that temporary node will be the header, because remember, at the very beginning, and you look at the linked list only has the header node. With header node, we're able to access every other node in the linked list. So in the else part, what I'm going to do, I'm going to create a temporary node. So I'm going to node, let's call it what is the current node, to be the header node. So I'm keeping the header node into a temporary node called current. And now, while the current node .next is not equal to null, I'm gonna traverse the node, traverse the linked list, and go to the next one. How can I do that? Just one moment. So it's gonna be current will be equal to current node dot next. So let's see that how usually it works. At first, I said put the current node to be head. So that's the current node. And I said while the current node dot next is not equal to null, which in this case is not, update the current node to be the current dot next, which is in this case this one. So now this is not the current one anymore. This one is the current one. Then it goes back to the while loop at the very beginning of the while loop again, and it says while current dot next is not equal to null, do the same thing. So as you see, it is not null, so it's not current anymore, and this node here over here will be the current node. So, and now here it says while current dot next is not equal to null, which in this case it is null, it does not exist. So it means our while loop condition is not valid anymore, and we are exiting, and we're gonna stay here. So now we need to see what happened. We were able to find the very last node by traversing the linked list and using the temporary node current node, which now again points to the very last one. So let's see that how usually it works. This last node needs to point to the node n, because we're gonna insert the node n to be the very last one. So we need to create that connection. So I'm going to write current.next is equal to n. So I created that connection, and I think we're good to go, and there's no change in the header because node n was inserted at the very end of the node. So in the next video, I will show you the methods called pop back and also pop front, which will be used to remove a node from the very beginning of the linked list and from very end of a linked list. Before we end this video, I'm going to also talk about the time complexity of these two operations, which are push front and push back. So I'm going to go back to this code that we wrote for the push front. As you see here, for the push front, we had an if statement here, and we checked if the header is null or not. If it wasn't, then we're inserting the. If it was, we assigning the head to be the new node. Otherwise, we do write some statement in order to insert that. That's the code that you see here. So these codes, I'm just gonna just make it like more readable, was the code that for the case that the linked list was not empty. As you see, the number of operations are constant, which means that the push front operation in a single linked list has a time complexity of big O of 1. Again, 1 does not mean that it is only one operation, but it means that it is a constant number operation which does not depend on the number of items in the linked list, or in other words, the input size. However, if you look at the pushback method, we had to write a while loop. This while loop was traversing the linked list from the very beginning up to the very end of the linked list. So we had to write the current while the current node is next is not equal to null. So, and because that means that it needs to go to the whole linked list, so we had to do n traversal, and again, n is the number of items in the linked list, or in other words, the size of the linked list. So the time complexity in order to do the pushback in the worst case can be the big O of n, assuming the linked list is not empty. If the linked list is empty, again, the number of operation is constant, which is going to be big O of 1. So we can say that in the worst case, a single linked list does big O of n for the pushback and big O of 1 for the push front.